Okay, let's unpack this. Welcome to the deep dive.
Glad to be here.
Today we're diving into a set of sources focusing on the fundamental rules of exponents, the real bedrock stuff.
That's right. We've got material here that, essentially gives us the core toolkit for handling powers and roots, showing how things that look pretty complex on the surface can actually be, well, dramatically simplified.
Exactly. So think of our mission for this deep dive as building that toolkit rule by rule, straight from the source material.
Yeah.
We want to see how these laws provide like a powerful shortcut, a way to cut through potentially massive calculations.
And find the elegant answer, right. And what's fascinating, I think, is how these rules just sort of emerge logically from the basic definition of a power.
How so?
Well, if 6 nuller just means multiplying x by itself on times, then the rules for combining these, they start to make intuitive sense.
Okay, yeah, and they immediately give you shortcuts. So first up, the product law.
Right.
The sources show when times and am plus not, so multiplying terms, same base.
Just add the exponents.
Simple as that.
Yeah.
No need to calculate, say, $37 and $37 separately just to multiply them. $37 times 343 is just, boom, 3 different sevens.
Tool number 1 right there for combining terms.
Exactly.
And, well, if multiplication means adding exponents, it kind of stands to reason that division.
Would be the opposite. Subtraction.
Precisely. The quotient law, as shown in the sources, gives us fracum. You subtract the exponents.
Okay, and this is where it gets really interesting, actually, because that quotient rule helps explain some key special cases.
Like 0 exponents.
Yeah. What happens if the exponents are the same? You get frac am, which the rule says is AMN, or $8.
But anything non-zero divided by itself is just 1.
Right. So that immediately tells us why any non-zero number to the power of 0, $8
Yeah.
must equal 1. It's like a direct consequence.
It falls right out of the rule. And it also explains negative exponents, too.
How does that work?
Well, look at that example from the source. Frac by the quotient rule, that's 6 by 11, which is 6/3. But if you write it out the long way, like fractions, frac c dot x c dot x, c dot x c dot x c dot, c dot x I dot x, c dot x c dot, you cancel 5 x's top and bottom.
And you're left with 3 x's on the bottom. So factoid a equals fractoid f a. So 6/3 equals frac 1 by 3, and that reveals the general rule, A, B, C day.
Got it. So a negative exponent just means take the reciprocal, make the exponent positive. Neat.
Exactly.
Okay, so we have tools for multiplying, dividing, same bases, plus 0 and negative exponents. What about a power of a power?
Ah, yes. The power law. The source is stated as AMN.
So when you raise a power to another power, you just multiply the exponents.
That's it. So something like $37 for 4 becomes 37 times 4, which is 328.
Imagine trying to calculate 37 another first, then raising that huge number to the 4th power.
Yeah, no thanks. This rule is a massive shortcut.
Definitely.
And the sources also cover exponents acting on products or quotients inside parentheses.
Oh, right, like A times BNN, N times BNN.
Yeah.
And the division version, too. Essentially, the exponent distributes over multiplication or division.
Which you absolutely need for expressions like A5 by B342. You'd use this rule first.
Yep. Apply this rule first, then the power law we just talked about. So A5 4 saws, B4 saw.
Which gives a $20 B12.
But see how the rules stack?
Yeah, it's like building blocks. And finally, there's one that ties together two things that seem different. Fractional exponents.
Right. This one's really elegant. The sources show a
So it connects roots and powers directly. The denominator of the fraction is the read index.
And the numerator is the power. So square piton is just $512.
And something like squared 657 is 576.5.
Wow. And the beauty is this single rule lets you use all the same exponent laws we just discussed for roots as well.
It brings everything under one roof.
Yeah.
Very cool.
It really does. And if we, connect this to the bigger picture, these rules are fundamentally about simplification.
Makes sense.
Take a really messy expression, like maybe frac by 2, y3, 4x, 1, y5. Without these rules, good luck.
Yeah, that looks pretty daunting. But with our toolkit, first, that power rule on top.
Right. By a 2, y4 becomes 6 by 3, 4, 3.
Which is 6 by 85 goal. So the whole thing is now frac by $8, y, and y5
Much better. Now use the quotient rule for each base separately.
Okay, so for the x's, it's 6 by $8, the $6
And for the y's.
y12 $5, that's y17.
Yeah.
So we have 6 by y17.
Almost there.
at all.
Just need to handle that negative exponent on the y.
Right, the reciprocal rule, y17 and 2y17. So the final answer is frac by y17.
Exactly. Look how that complex fraction simplified right down.
That really shows the power of this toolkit in action.
It's not just about knowing the individual rules, it's seeing how they combine, how they interact.
So wrapping up then, we've seen how these fundamental laws combining powers, powers of powers, the rules for zero, negative, and fractional exponents, they don't just exist in isolation.
No, they work together systematically, just like the source material lays out.
And they give you the power to manipulate and really simplify expressions that would otherwise be, well, intractable.
They truly are the keys, you could say, to unlocking these kinds of problems. They let you work with numbers and variables efficiently, doesn't matter how large or small the exponents get.
Absolutely. They're the foundation for so much more complex math down the line. So here's something to think about. How might really mastering these fundamental rules change the way you approach calculations involving, say, exponential growth or decay?
Good question. Think about science, finance.
Anywhere where really big or really small numbers pop up. These aren't just rules, they're more like a language, right? A language for describing relationships and change.